All right, ready to dive into some fascinating math? We're going to be uncovering the world of polynomials today.
Polynomials.
Yeah, using polynomials.pdf as our guide. I think what's so cool about this is, polynomials pop up all the time in math, right? It's not like we're charting some undiscovered territory here.
Right.
But what makes them so interesting is that there's these hidden depths to them, these little secrets about how they behave.
Yeah. They seem kind of simple on the surface.
Yeah.
Just variables and exponents mixed and matched.
Right.
But underneath, there's this whole intricate structure.
It's like a code waiting to be cracked.
Exactly.
So, okay, let's break it down a bit. Polynomial, what are we even talking about here?
Well, think back to your algebra classes.
Okay.
2x plus 3.
Okay.
Or 5x of 4 by 7 plus 2 plus by 2 through. Those are polynomials.
Those are our players in this game.
Exactly. And what's fascinating is that it's those subtle things about them, like their degree, the highest power of a variable, that give us clues about their hidden world.
It's like the higher the degree, the more secrets are hidden.
In a way, yes.
That's cool. So our source mentions different types of polynomials, almost like sizes.
Oh, I like that.
Yeah. We've got the linear ones, degree 1. Those are kind of like the small size.
Like a small polynomial? I
Right.
like that. Yeah, 2 by 3. That's a linear polynomial, degree 1.
Exactly. Then we level up to medium size, or quadratics, degree 2. Think x 3 by 4.
And then, of course, you get your large, we can't forget those, the cubics, degree 3.
So if I'm understanding this right, something like 2x, that fits in the cubic category.
Absolutely, you got it. And here's where things get even more interesting. That size you mentioned, the degree, it's not just a name. It actually hints at something pretty important about the polynomial. It gives us clues about its solutions, what mathematicians call the zeros.
Okay, zeros. I've always thought that sounded kind of mysterious. Why not just call them solutions?
Well, in math, a zero of a polynomial, it's a special input for x. When you plug it in, it makes the whole expression equal to 0.
So it's not about solving for x, it's about finding the x that makes it all just disappear.
Exactly. Vanish, like it never was there.
Okay, that does sound more intriguing than just solution. I'm into that. Now, in our source, they use x 3 by 4 of it as an example, and then they break it down into its factors, kind of like its fundamental building blocks, to get by 4x plus 1. So what's the connection there? What do those factors have to do with these elusive zeros?
That is the key insight. The factors, they directly reveal the zeros.
Really?
Yeah.
So let me see if I get this. If x plus 4 is a factor, then when x 4, the whole thing becomes 0.
Yes.
And same for the x plus 1, it leads us to x subpopulation is plus 1. So x 1 and 4 are our zeros.
Precisely. You've got it.
Wow, it all clicks into place. Now, I'm starting to visualize this, and I think it's time we brought in the graphs.
Yeah.
Graphs, because they give us that visual representation, right?
Yeah. Exactly. They make it so clear. Remember, zeros, those are the x values that make the polynomial equal 0, right?
Right, like finding those magic s.
Exactly. On a graph, those zeros, they're the points where the curve actually crosses the x-axis. It's like visually, that's where the polynomial hits 0.
And our source even has figures to show this 2.2 through 2.8. And you can see it. For y-axis 3 by 4 money, the graph, it intersects the x-axis and -1 and 4, those zeros we just talked about. It's all connected.
It's beautiful how it all comes together.
It is. It is. And what's really cool is that even the degree, that seemingly simple number, it plays a crucial role here too. It tells us how many times, at most, the graph can cross the x-axis, which means it also tells us the maximum number of zeros we can have.
It's like the polynomial structure is giving us these hints, revealing its secrets.
Its degree, its factors, it's all related.
And it gets even more interesting. We can actually take this a step further and look at the connection between the zeros and the coefficients, those numbers that are hanging out in front of the variables.
Okay.
There's a fascinating link there.
Coefficients, okay. Those numbers always seemed kind of, I don't know, just kind of there. Like, what's their deal? How do they connect to the zeros?
It's pretty amazing, actually. Let's say we've got ourselves a nice quadratic polynomial, something like x plus bx plus c.
Yes.
So a, b, and c, those are our coefficients, right?
Right.
Hanging out, doing their thing. But here's the thing. They actually have a direct link to the zeros of that quadratic. Let's call those zeros ion pull, just for fun.
Okay, so you're saying just by knowing A, B, and C, we can figure stuff out about ion pull.
Exactly. It's like a little mathematical puzzle.
I like it.
Think back to how we factor quadratics. Remember those nice little x terms we get?
Yeah.
Well, if we take those factors and multiply them out, something really cool happens.
What's that?
We see that b, that coefficient of our x term, it's actually the same as the negative sum of our zeros.
So like, wait,
Exactly. And C, our constant term, that's just the product of the zeros.
Wait, hold on. So if I add up the zeros of a quadratic, flip the sign, I get B.
Yep.
And if I multiply the zeros together, I get C.
You got it. It's like magic, but it's math. And our source has some great examples of this. Example 2, for instance, uses x soup plus 7x plus 10.
Oh yeah, the one where we found the zeros were -2 and -5.
That's the one.
So if I add those, I get -7, flip the sign, and boom, 7. And if I multiply them, -2 times -5, that's 10. It's like those coefficients were hiding the answers all along.
Exactly. It's like they can't help but reveal the secrets of the zeros.
This is awesome. So if this works for quadratics, what about the more complex ones, like our cubics? Does the same kind of thing happen there?
Cubics, absolutely. They're a bit more intricate, of course. We've got 3 zeros to juggle now, ABBA and AC. But the source in example 5 shows us that the sum of those zeros that's still related to our coefficients, specifically AB.
So that pattern holds. What about the products of the zeros in cubics?
Well, when we look at all the pairs we can make that's ABBA and AC and add those products up, guess what? That's equal to AC.
Okay, so there's a pattern there too with the coefficients. Cool. But what about multiplying all 3 zeros together?
That's where it gets really interesting. Multiply LA and OW, and you get ETA.
Is being that constant term at the end of our cubics.
You got it.
Yeah.
XOLs plus BXOL plus CX plus D, it all ties together.
So even with cubics, those coefficients, they're like little clues leading us to the zeros. This is amazing.
It really highlights how deeply connected everything is in math.
It's like a secret code.
And just like cracking a code can unlock a hidden message, understanding these relationships, it gives us a deeper understanding of how polynomials work.
It's like a whole new way of looking at math, you know?
It really is. It's about seeing those connections, those underlying patterns.
Exactly. And speaking of patterns, our source keeps going deeper with this, talking about dividing polynomials. That sounds kind of intense, right? Like we're going beyond just adding and multiplying now.
It's a powerful tool. Kind of like we're using math to, I don't know, dissect a polynomial, really see what makes it tick.
Okay, I like that. Our source calls it the division algorithm for polynomials, and it basically says that if you've got a polynomial, say px, and you divide it by another one, let's call that gx, our divisor. It sounds fancy, but we always end up with two things: a quotient, qx, and a remainder, rx. So it is like regular division then, huh?
Exactly. Sometimes that remainder is 0, which means our divisor, it divides perfectly into the original polynomial. But sometimes we have a little leftover.
Leftovers. Makes sense. I see here in the source, they even give examples of how to actually do the division, like dividing, let me see, 3xx plus 5 foot by Omara by 1 xxs. Looks a little complicated, but
I can see them that way, yeah.
But the main point is we can do it. And it helps us break down these polynomials even further, right?
That's the key. It's not so much about becoming polynomial division experts, but about understanding what this tool lets us do.
Right. It's like adding another tool to our toolkit. Like we've got our factoring, our graphing, and now we're dividing.
Exactly.
And they all work together to help us uncover the secrets of these polynomials. Like example 9, it uses division to actually find all the zeros, you know, and we already know some of them.
It all ties together.
It really does. This whole deep dive, it's been like mind-blowing in a way. Who knew there was so much to uncover about these things?
It's fascinating, isn't it?
It is. It's like that question I had earlier about working backward from the zeros to find the original polynomial. It makes you realize just how interconnected all of this is.
Exactly. And that's what's so exciting about math, really. It's all about recognizing those patterns, making those connections.
It's like a whole new world opens up when you start to see it.
Absolutely. And the best part is there's always more to discover.
Always more to learn. Well, on that note, I think we've done some serious deep diving today.
We have. It's been a pleasure exploring this with you.
Likewise. And to everyone listening, thanks for joining us on this mathematical adventure. Keep those brains engaged, keep asking questions, and who knows what amazing things you'll uncover. Until next time.